It suggests new avenues of research to professionals, and it provides a succinct organization of the whole of chemistry. It is a remarkable demonstration of the fact that the chemical elements are not a random cluster of entities but instead display trends and lie together in families. An awareness of the periodic table is essential to anyone who wishes to disentangle the world and see how it is built up from the fundamental building blocks of the chemistry, the chemical elements. Glenn T. Sayerborg. In this unit, we will study the historical development of the periodic table as it stands today and the modern periodic law. We will also learn how the periodic classification follows as a logical consequence of the electronic configuration of atoms. Finally, we shall examine some of the periodic trends in the physical and chemical properties of the elements. 3.1 Why do we need to classify elements? We know by now that the elements are the basic units of all types of matter. In 1800, only 31 elements were known. By 1865, the number of identified elements had more than doubled to 63. At present 114 elements are known. Of them, the recently discovered elements are man-made. Efforts to synthesize new elements are continuing. With such a large number of elements, it is very difficult to study individually the chemistry of all these elements and their innumerable compounds individually. To ease out this problem, scientists searched for a systematic way to organize their knowledge by classifying the elements. Not only that it would rationalize known chemical facts about elements, but even predict new ones for undertaking further study. Unit 3 After studying this unit, you will be able to appreciate how the concept of grouping elements in accordance to their properties led to the development of periodic table. Understand the periodic law. Understand the significance of atomic number and electronic configuration as the basis for periodic classification. Name the elements with Z. 100 according to IUPAC nomenclature. Classify elements into S, P, D, F blocks and learn their main characteristics. Recognize the periodic trends in physical and chemical properties of elements. Compare the reactivity of elements and correlate it with their occurrence in nature. Explain the relationship between ionization enthalpy and metallic character. Use scientific vocabulary appropriately to communicate ideas related to certain important properties of atoms, e.g., atomic ionic radii, ionization enthalpy, electron gain enthalpy, electronegativity, valence of elements. Classification of elements and periodicity in Properties 2019-20. Classification of elements and periodicity in Properties 3.2 Genesis of periodic classification. Classification of elements into groups and development of periodic law and periodic table are the consequences of systematizing the knowledge gained by a number of scientists through their observations and experiments. The German chemist Johann Dobereiner in early 1800s was the first to consider the idea of trends among properties of elements. By 1829 he noted a similarity among the physical and chemical properties of several groups of 3 elements, triads. In each case, he noticed that the middle element of each of the triads had an atomic weight about halfway between the atomic weights of the other 2. Table 3.1. Also the properties of the middle element were in between those of the other 2 members. Since Dobereiner's relationship, referred to as the law of triads, seemed to work only for a few elements, it was dismissed as coincidence. The next reported attempt to classify elements was made by a French geologist, Aimé de Chancourtois, in 1862. He arranged the then known elements in order of increasing atomic weights and made a cylindrical table of elements to display the periodic recurrence of properties. This also did not attract much attention. The English chemist, John Alexander Newlands, in 1865 propounded the law of octaves. He arranged the elements in increasing order of their atomic weights and noted that every eighth element had properties similar to the first element, Table 3.2. The relationship was just like every eighth note that resembles the first in octaves of music. Newlands's law of octaves seemed to be true only for elements up to calcium. Although his idea was not widely accepted at that time, he, for his work, was later awarded Dovey Medal in 1887 by the Royal Society, London. The periodic law, as we know it today, owes its development to the Russian chemist, Dmitry Mendeleev, 1834–1907, and the German chemist, Lothar Meyer, 1830–1895. Working independently, both the chemists in 1869 proposed that on arranging elements in the increasing order of their atomic weights, similarities appear in physical and chemical properties at regular intervals. Lothar Meyer plotted the physical properties such as atomic volume, melting point and boiling point against atomic weight and obtained a periodically repeated pattern. Unlike Newlands, Lothar Meyer observed a change in length of that repeating pattern. By 1868, Lothar Meyer had developed a table of the atomic weight Li 7 Ca40 close 35.5 Na 23 senior 88 Br 80 K 39 Ba 137 I 127 Table 3.1 Dobereiner's triads Table 3.2 Newlands octaves element Li BBC NOF at Wt 7911 12 14 16 19 element Na MgL Psi PsCl at Wt 23 24 27 29 31 32 35.5 element Kca at Wt 39 42,000 and 19 to 20. 76 chemistry elements that closely resembles the modern periodic table. However, his work was not published until after the work of Dmitry Mendeleev, the scientist who is generally credited with the development of the modern periodic table. While Dobereiner initiated the study of periodic relationship, it was Mendeleev who was responsible for publishing the periodic law for the first time. It states as follows: the properties of the elements are a periodic function of their atomic weights. Mendeleev arranged elements in horizontal rows and vertical columns of a table in order of their increasing atomic weights in such a way that the elements with similar properties occupied the same vertical column or group. Mendeleev's system of classifying elements was more elaborate than that of Lothar Meyer's. He fully recognized the significance of periodicity and used broader range of physical and chemical properties to classify the elements. In particular, Mendeleev relied on the similarities in the empirical formulas and properties of the compounds formed by the elements. He realized that some of the elements did not fit in with his scheme of classification if the order of atomic weight was strictly followed. He ignored the order of atomic weights, thinking that the atomic measurements might be incorrect, and placed the elements with similar properties together. For example, Iodine with lower atomic weight than that of tellurium, group 6, was placed in group 7 along with fluorine, chlorine, bromine because of similarities in properties, Fig 3.1. At the same time, keeping his primary aim of arranging the elements of similar properties in the same group, he proposed that some of the elements were still undiscovered and, therefore, left several gaps in the table. For example, both gallium and germanium were unknown at the time Mendeleev published his periodic table. He left the gap under aluminium and a gap under silicon, and called these elements Aka-aluminium and Aka-silicon. Mendeleev predicted not only the existence of gallium and germanium, but also described some of their general physical properties. These elements were discovered later. Some of the properties predicted by Mendeleev for these elements and those found experimentally are listed in Table 3.3. The boldness of Mendeleev's quantitative predictions and their eventual success made him and his periodic table famous. Mendeleev's periodic table published in 1905 is shown in Fig. 3.1. Property Aka-aluminium gallium Aka-silicon germanium, predicted, found, atomic weight 68 70 72 72.6 density, GCM3, 5.9 5.94 5.55.36 melting point Kilo 302.93 high 1231 formula of oxide E2O3 Ga2O3 EO2 GO2 formula of chloride ECl3 GaCl3 ECl4 GeCl4 Table 3.3 Mendeleev's predictions for the elements Aka-aluminium, gallium, and Aka-silicon, germanium, 2019-20. 77 Classification of elements and periodicity in proper ties periodic system of the elements in groups and series Fig. 3.1 Mendeleev's periodic table published earlier 2019-20. 78 Chemistry 3.3 Modern periodic law and the present form of the periodic table. We must bear in mind that when Mendeleev developed his periodic table, chemists knew nothing about the internal structure of atom. However, the beginning of the 20th century witnessed profound developments in theories about subatomic particles. In 1913, the English physicist Henry Moseley observed regularities in the characteristic X-ray spectra of the elements. A plot of nu, where nu is frequency of X-rays emitted, against atomic number, Z, gave a straight line and not the plot of nu versus atomic mass. He thereby showed that the atomic number is a more fundamental property of an element than its atomic mass. Mendeleev's periodic law was, therefore, accordingly modified. This is known as the modern periodic law and can be stated as, the physical and chemical properties of the elements are periodic functions of their atomic numbers. The periodic law revealed important analogies among the 94 naturally occurring elements. Neptunium and plutonium like actinium and protoactinium are also found in pitchblende and ore of uranium. It stimulated renewed interest in inorganic chemistry and has carried into the present with the creation of artificially produced short-lived elements. You may recall that the atomic number is equal to the nuclear charge, i.e., number of protons, or the number of electrons in a neutral atom. It is then easy to visualize the significance of quantum numbers and electronic configurations in periodicity of elements. In fact, it is now recognized that the periodic law is essentially the consequence of the periodic variation in electronic configurations, which indeed determine the physical and chemical properties of elements and their compounds. Numerous forms of periodic table have been devised from time to time. Some forms emphasize chemical reactions and valence, whereas others stress the electronic configuration of elements. A modern version, the so-called long form of the periodic table of the elements, Fig 3.2, is the most convenient and widely used. The horizontal rows, which Mendeleev called series, are called periods, and the vertical columns, groups. Elements having similar outer electronic configurations in their atoms are arranged in vertical columns, referred to as groups or families. According to the recommendation of International Union of Pure and Applied Chemistry, IUPAC, the groups are numbered from 1 to 18, replacing the older notation of groups IA, VIIA, 8, IB, 8IB and 0. There are altogether 7 periods. The period number corresponds to the highest principal quantum number, n, of the elements in the period. The first period contains 2 elements. The subsequent periods consists of 8, 8, 18, 18 and 32 elements, respectively. The 7th period is incomplete and, like the 6th period, would have a theoretical maximum, on the basis of quantum numbers, of 32 elements. In this form of the periodic table, 14 elements of both 6th and 7th periods, lanthanoids and actinoids, respectively, are placed in separate panels at the bottom. 3.4 Nomenclature of elements with atomic numbers 100. The naming of the new elements had been traditionally the privilege of the discoverer, or discoverers, and the suggested name was ratified by the IUPAC. In recent years this has led to some controversy. The new elements with very high atomic numbers are so unstable that only minute quantities, sometimes only a few atoms of them, are obtained. Their synthesis and characterization, therefore, require highly ** Lenty Seaborg's work in the middle of the 20th century, starting with the discovery of plutonium in 1940, followed by those of all the transuranium elements from 94 to 102, led to reconfiguration of the periodic table, placing the actinoids below the lanthanoids. In 1951, Seaborg was awarded the Nobel Prize in Chemistry for his work. Element 106 has been named Seaborgium, Sg, in his honor. 2019-20. 79 Classification of elements and periodicity in properties. Fig. 3.2 Long form of the periodic table of the elements with their atomic numbers and ground state outer electronic configurations. The groups are numbered 1 to 18 in accordance with the 1984 IUPAC recommendations. This notation replaces the old numbering scheme of IA, VIIA, 8, IB, 8IB and 0 for the elements. 2019-20. 80 Chemistry, sophisticated costly equipment and laboratory. Such work is carried out with competitive spirit only in some laboratories in the world. Scientists, before collecting the reliable data on the new element, at times get tempted to claim for its discovery. For example, both American and Soviet scientists claimed credit for discovering element 104. The Americans named it Rutherfordium, whereas Soviets named it Kuchathavium. To avoid such problems, the IUPAC has made recommendation that until a new element's discovery is proved, and its name is officially recognized, a systematic nomenclature be derived directly from the atomic number of the element using the numerical roots for 0 and numbers 1 to 9. These are shown in Table 3.4. The roots are put together in order of digits, atomic name according to symbol IUPAC, IUPAC number, IUPAC nomenclature, official name symbol 100 and 1 unnilunium anu mendelevium MD 100 and 2 unnilbium and nobelium number 100 and 3 unniltrium and lawrencium LR 100 and 4 unnilquodium and rutherfordium RF 100 and 5 unnilpentium and dubnium DB 100 and 6 unnilhexium and seaborgium SG 100 and 7 unnilseptium and bohrium BH 100 and 8 unniloctium UNOHuscium HS 100 and 9 unnilenium and metnerium metricton 100 and 10 unnillium and darmstadtium DS 100 and 11 ununium UUU. Rontgenium RG 100 and 12 ununbium ut copernicium CN 100 and 13 ununtrium ut neonium NH 100 and 14 ununquodium ut flarovium FL 100 and 15 ununpentium up moscovium MC 100 and 16 ununhexium a livermorium LV 100 and 17 ununseptium us tennescentes 100 and 18 ununoctium UU organism octable 3.5 Nomenclature of elements with atomic number above 100. Table 3.4 Notation for IUPAC. Nomenclature of elements which make up the atomic number and ium is added at the end. The IUPAC names for elements with Z above 100 are shown in Table 3.5. Digit name abbreviation 0 nil N1 N U2 by B3 3 T4 quad Q5 pent P6 hex 8 7th September S 8th October 09 NE 2019 to 20. Classification of elements and periodicity in properties. Thus, the new element first gets a temporary name, with symbol consisting of 3 letters. Later permanent name and symbol are given by a vote of IUPAC representatives from each country. The permanent name might reflect the country, or state of the country, in which the element was discovered, or pay tribute to a notable scientist. As of now, elements with atomic numbers up to 118 have been discovered. Official names of all elements have been announced by IUPAC. Problem 3.1 What would be the IUPAC name and symbol for the element with atomic number 120? Solution from Table 3.4. The roots for 1, 2 and 0 are un, bi and nil, respectively. Hence, the symbol and the name respectively are UBN and unbenilium. 3.5 Electronic configurations of elements and the periodic table. In the preceding unit we have learned that an electron in an atom is characterized by a set of 4 quantum numbers, and the principal quantum number, n, defines the main energy level known as shell. We have also studied about the filling of electrons into different subshells, also referred to as orbitals, s, p, d, f, in an atom. The distribution of electrons into orbitals of an atom is called its electronic configuration. An element's location in the periodic table reflects the quantum numbers of the last orbital filled. In this section we will observe a direct connection between the electronic configurations of the elements and the long form of the periodic table. Electronic configurations in periods. The period indicates the value of n for the outermost or valence shell. In other words, successive period in the periodic table is associated with the filling of the next higher principal energy level, n is equal to 1, n is equal to 2, etc. It can be readily seen that the number of elements in each period is twice the number of atomic orbitals available in the energy level that is being filled. The first period, n is equal to 1, starts with the filling of the lowest level, 1s, and therefore has 2 elements, hydrogen, Ls1, and helium, Ls2, when the first shell, K, is completed. The second period, n is equal to 2, starts with lithium and the third electron enters the 2s orbital. The next element, Beryllium has 4 electrons and has the electronic configuration 1s22s2. Starting from the next element boron, the 2p orbitals are filled with electrons when the L shell is completed at neon, 2s22p6. Thus there are 8 elements in the second period. The third period, n is equal to 3, begins at sodium, and the added electron enters a 3s orbital. Successive filling of 3s and 3p orbitals gives rise to the third period of 8 elements from sodium to argon. The fourth period, n is equal to 4, starts at potassium, and the added electrons fill up the 4s orbital. Now you may note that before the 4p orbital is filled, filling up of 3d orbitals becomes energetically favorable and we come across the so-called 3d transition series of elements. This starts from scandium, Z is equal to 21, which has the electronic configuration 3d14s2. The 3d orbitals are filled at zinc, Z is equal to 30, with electronic configuration 3d104s2. The fourth period ends at krypton with the filling up of the 4p orbitals. Altogether we have 18 elements in this fourth period. The fifth period, n is equal to 5, beginning with rubidium is similar to the fourth period and contains the 4d transition series starting at yttrium, Z is equal to 39. This period ends at xenon with the filling up of the 5p orbitals. The sixth period, n is equal to 6, contains 32 elements and successive electrons enter 6s4f5d and 6p orbitals, in the order, filling up of the 4f orbitals begins with cerium, Z is equal to 58, and ends at lutetium, Z is equal to 71, to give the 4f inner transition series which is called the lanthanoid series. The seventh period, n is equal to 7, is similar to the sixth period with the successive filling up of the 7s5f6d and 7p orbitals and includes most of the man-made radioactive elements. This period will end at the element with atomic number 118 which would belong to the noble gas family. Filling up of the 5f orbitals after actinium, Z is equal to 89, gives the 5f inner transition 2019 to 20. 82 chemistry series known as the actinoid series. The 4f and 5f inner transition series of elements are placed separately in the periodic table to maintain its structure and to preserve the principle of classification by keeping elements with similar properties in a single column. Problem 3.2 How would you justify the presence of 18 elements in the fifth period of the periodic table? Solution: when n is equal to 5, L is equal to 0, 1, 2, 3. The order in which the energy of the available orbitals 4d 5s and 5p increases is 5s, 4d, 5p. The total number of orbitals available are 9. The maximum number of electrons that can be accommodated is 18, and therefore 18 elements are there in the fifth period. B. Groupwise electronic configurations. Elements in the same vertical column or group have similar valence shell electronic configurations, the same number of electrons in the outer orbitals, and similar properties. For example, the group 1 elements, alkali metals, all have ns1 valence shell electronic configuration as shown below. Atomic number symbol electronic configuration 3 Li 1s22s1, or He 2s111 Na 1s22 2s22 p6 3s1, or Ne 3s119 K1 s22 s22 p6 3s2 3p6 4s1, or Ar 4 S137 RB1 S22 S22 P63 S23 P63 D1 04 S24 P65 S1, or Kr. 5 S155 CS1 S22 S22 P63 S23 P63 D1 04 S24 P64 D1 05 S25 P66 S1, or XE. 6 S187 FR, RN. 7 S1 Theoretical foundation for the periodic classification. The elements in a vertical column of the periodic table constitute a group or family and exhibit similar chemical behavior. This similarity arises because these elements have the same number and same distribution of electrons in their outermost orbitals. We can classify the elements into 4 blocks viz. S block, P block, D block and F block depending on the type of atomic orbitals that are being filled with electrons. This is illustrated in Fig. 3.3. We notice 2 exceptions to this categorization. Strictly, helium belongs to the S block, but its positioning in the P block along with other group 18 elements is justified because it has a completely filled valence shell, 1s2, and as a result, exhibits properties characteristic of other noble gases. The other exception is hydrogen. It has only one s electron and hence can be placed in group 1, alkali metals. It can also gain an electron to achieve a noble gas arrangement and hence it can behave similar to a group 17, halogen family, elements. Because it is a special case, we shall place hydrogen separately at the top of the periodic table as shown in Fig. 3.2 and Fig. 3.3. We will briefly discuss the salient features of the 4 types of elements marked in. Thus it can be seen that the properties of an element have periodic dependence upon its atomic number and not on relative atomic mass. 3.6 Electronic configurations and types of elements. S, P, D, F blocks. The Aufbau, build-up, principle and the electronic configuration of atoms provide the periodic table. More about these elements will be discussed later. During the description of their features, certain terminology has been used which has been classified in section 3.7. 3rd June 2001. The S block elements. The elements of group 1, alkali metals, and group 2, alkaline earth metals, which have NS1 2019-20. 83 Classification of elements and periodicity in proper ties. NH McTSOG Fig. 3.3 The types of elements in the periodic table based on the orbitals that are being filled. Also shown is the broad division of elements into metals, nonmetals, and metalloids. 2019-20. 84 Chemistry and NS2 outermost electronic configuration belong to the S block elements. They are all reactive metals with low ionization enthalpies. They lose the outermost electron, S, readily to form 1+ ion, in the case of alkali metals, or 2+ ion, in the case of alkaline earth metals. The metallic character and the reactivity increase as we go down the group. Because of high reactivity, they are never found pure in nature. The compounds of the S block elements, with the exception of those of lithium and beryllium, are predominantly ionic. 3rd June 2002. The P block elements. The P block elements comprise those belonging to group 13 to 18, and these together with the S block elements are called the representative elements or main group elements. The outermost electronic configuration varies from Ns2Np1 to Ns2Np6 in each period. At the end of each period is a noble gas element with a closed valence shell Ns2Np6 configuration. All the orbitals in the valence shell of the noble gases are completely filled by electrons, and it is very difficult to alter this stable arrangement by the addition or removal of electrons. The noble gases thus exhibit very low chemical reactivity. Preceding the noble gas family are two chemically important groups of nonmetals. They are the halogens, group 17, and the chalcogens, group 16. These two groups of elements have highly negative electron gain enthalpies and readily add 1 or 2 electrons respectively to attain the stable noble gas configuration. The nonmetallic character increases as we move from left to right across a period, and metallic character increases as we go down the group. 3rd June 2003. The D block elements, transition elements. These are the elements of group 3 to 12 in the center of the periodic table. These are characterized by the filling of inner d orbitals by electrons and are therefore referred to as d block elements. These elements have the general outer electronic configuration N-1, D1-10 NS0-2. They are all metals. They mostly form colored ions, exhibit variable valence, oxidation states, paramagnetism, and oftenly used as catalysts. However, Zn, Cd and Hg, which have the electronic configuration N-1, D10 NS2, do not show most of the properties of transition elements. In a way, transition metals form a bridge between the chemically active metals of S block elements and the less active elements of groups 13 and 14, and thus take their familiar name, transition elements. 3rd June 2004. The F block elements, inner transition elements, the two rows of elements at the bottom of the periodic table, called the lanthanoids, Ce, Z is equal to 58, Lu, Z is equal to 71, and actinoids, Eth, Z is equal to 90, Lr, Z is equal to 103, are characterized by the outer electronic configuration N-2, F1-14, N-1, D01 NS2. The last electron added to each element is filled in F orbital. These two series of elements are hence called the inner transition elements, F block elements. They are all metals. Within each series, the properties of the elements are quite similar. The chemistry of the early actinoids is more complicated than the corresponding lanthanoids, due to the large number of oxidation states possible for these actinoid elements. Actinoid elements are radioactive. Many of the actinoid elements have been made only in nanogram quantities or even less by nuclear reactions, and their chemistry is not fully studied. The elements after uranium are called transuranium elements. Problem 3.3. The elements Z is equal to 117 and 120 have not yet been discovered. In which family group would you place these elements, and also give the electronic configuration in each case? Solution. We see from Fig. 3.2 that element with Z is equal to 117 would belong to the halogen family, group 17, and the electronic configuration would be Rn 5F146D107S27P5. The element with Z is equal to 120 will be placed in group 2, alkaline earth metals, and will have the electronic configuration UO 8S2. 2019-20. Classification of elements and periodicity in proper ties. 3rd June 2005. Metals, nonmetals and metalloids. In addition to displaying the classification of elements into S, P, D, and F blocks, Fig. 3.3 shows another broad classification of elements based on their properties. The elements can be divided into metals and nonmetals. Metals comprise more than 78% of all known elements and appear on the left side of the periodic table. Metals are usually solids at room temperature. Mercury is an exception. Gallium and cesium also have very low melting points, 303 K and 302 K respectively. Metals usually have high melting and boiling points. They are good conductors of heat and electricity. They are malleable, can be flattened into thin sheets by hammering, and ductile, can be drawn into wires. In contrast, nonmetals are located at the top right-hand side of the periodic table. In fact, in a horizontal row, the property of elements change from metallic on the left to nonmetallic on the right. Nonmetals are usually solids or gases at room temperature with low melting and boiling points. Boron and carbon are exceptions. They are poor conductors of heat and electricity. Most nonmetallic solids are brittle and are neither malleable nor ductile. The elements become more metallic as we go down a group. The nonmetallic character increases as one goes from left to right across the periodic table. The change from metallic to nonmetallic character is not abrupt as shown by the thick zigzag line in Fig. 3.3. The elements, e.g., silicon, germanium, arsenic, antimony and tellurium, bordering this line and running diagonally across the periodic table show properties that are characteristic of both metals and nonmetals. These elements are called semimetals or metalloids. Problem 3.4. Considering the atomic number and position in the periodic table, arrange the following elements in the increasing order of metallic character: Psi, B, Mg, Na, P. Solution metallic character increases down a group and decreases along a period as we move from left to right. Hence the order of increasing metallic character is P, Psi, B, Mg, Na. 3.7. Periodic trends in properties of elements. There are many observable patterns in the physical and chemical properties of elements as we descend in a group or move across a period in the periodic table. For example, within a period, chemical reactivity tends to be high in group 1 metals, lower in elements towards the middle of the table, and increases to a maximum in the group 17 nonmetals. Likewise, within a group of representative metals, say alkali metals, reactivity increases on moving down the group, whereas within a group of nonmetals, say halogens, reactivity decreases down the group. But why do the properties of elements follow these trends? And how can we explain periodicity? To answer these questions, we must look into the theories of atomic structure and properties of the atom. In this section we shall discuss the periodic trends in certain physical and chemical properties and try to explain them in terms of number of electrons and energy levels. 3rd July 2001. Trends in physical properties. There are numerous physical properties of elements such as melting and boiling points, heats of fusion and vaporization, energy of atomization, etc., which show periodic variations. However, we shall discuss the periodic trends with respect to atomic and ionic radii, ionization enthalpy, electron gain enthalpy and electronegativity. Atomic radius. You can very well imagine that finding the size of an atom is a lot more complicated than measuring the radius of a ball. Do you know why? Firstly, because the size of an atom, 1.2 ai, 1.2 times 10 m in radius, is very small. Secondly, since the electron cloud surrounding the atom does not have a sharp boundary, the determination of the atomic size cannot be precise. In other words, there is no 2019 to 20. 86 Chemistry practical way by which the size of an individual atom can be measured. However, an estimate of the atomic size can be made by knowing the distance between the atoms in the combined state. One practical approach to estimate the size of an atom of a nonmetallic element is to measure the distance between two atoms when they are bound together by a single bond in a covalent molecule, and from this value, the covalent radius of the element can be calculated. For example, the bond distance in the chlorine molecule, Cl2, is 198 pm, and half this distance, 99 pm, is taken as the atomic radius of chlorine. For metals, we define the term metallic radius, which is taken as half the internuclear distance separating the metal cores in the metallic crystal. For example, the distance between two adjacent copper atoms in solid copper is 256 pm, hence the metallic radius of copper is assigned a value of 128 pm. For simplicity, in this book, we use the term atomic radius to refer to both covalent or metallic radius depending on whether the element is a nonmetal or a metal. Atomic radii can be measured by X-ray or other spectroscopic methods. The atomic radii of a few elements are listed in Table 3.6. Two trends are obvious. We can explain these trends in terms of nuclear charge and energy level. The atomic size generally decreases across a period as illustrated in Fig. 3.4a for the elements of the second period. It is because within the period the outer electrons are in the same valence shell and the effective nuclear charge increases as the atomic number increases, resulting in the increased attraction of electrons to the nucleus. Within a family or vertical column of the periodic table, the atomic radius increases regularly with atomic number as illustrated in Fig. 3.4b. For alkali metals and halogens, as we descend the groups, the principal quantum number, n, increases and the valence electrons are farther from the nucleus. This happens because the inner energy levels are filled with electrons, which serve to shield the outer electrons from the pull of the nucleus. Consequently, the size of the atom increases as reflected in the atomic radii. Note that the atomic radii of noble gases are not considered here. Being monoatomic, their non-bonded radii values are very large. In fact, radii of noble gases should be compared not with the covalent radii but with the van der Waals radii of other elements. Table 3.6a, Atomic radii pm across the periods. Table 3.6b, Atomic radii pm down a family atom, atomic, group I, radius, group 17, radius Li 152, floor 64, now 186, close 99, K 231, BR 114, RB 244, I 133, CS 262 at 140 atom, period 2. Li BBC NOF atomic radius 1521188 77 74 66 64 atom, period 3. Na MgL Psi PSCl atomic radius 186 143 117 110 104 99 2019 to 20. 87 Classification of elements and periodicity in properties. B. Ionic radius. The removal of an electron from an atom results in the formation of a cation, whereas gain of an electron leads to an anion. The ionic radii can be estimated by measuring the distances between cations and anions in ionic crystals. In general, The ionic radii of elements exhibit the same trend as the atomic radii. A cation is smaller than its parent atom because it has fewer electrons while its nuclear charge remains the same. The size of an anion will be larger than that of the parent atom because the addition of one or more electrons would result in increased repulsion among the electrons and a decrease in effective nuclear charge. For example, the ionic radius of fluoride ion, F, is 136 pm whereas the atomic radius of fluorine is only 64 pm. On the other hand, the atomic radius of sodium is 186 pm compared to the ionic radius of 95 pm for Na+. When we find some atoms and ions which contain the same number of electrons, we call them isoelectronic species star. For example, O2, F, Na+ and Mg2+ have the same number of electrons, 10. Their radii would be different because of their different nuclear charges. The cation with the greater positive charge will have a smaller radius because of the greater Fig. 3.4. A. Variation of atomic radius with atomic number across the second period Fig. 3.4. B. Variation of atomic radius with atomic number for alkali metals and halogens attraction of the electrons to the nucleus. An ion with the greater negative charge will have the larger radius. In this case, the net repulsion of the electrons will outweigh the nuclear charge and the ion will expand in size. Problem 3.5. Which of the following species will have the largest and the smallest size? Mg, Mg2+, L, L3+. Solution. Atomic radii decrease across a period. Cations are smaller than their parent atoms. Among isoelectronic species, the one with the larger positive nuclear charge will have a smaller radius. Hence the largest species is Mg, the smallest one is L3+. C. Ionization enthalpy. A quantitative measure of the tendency of an element to lose electron is given by its ionization enthalpy. It represents the energy required to remove an electron from an isolated gaseous atom, X, in its ground state. In other words, the first ionization enthalpy for an *2 or more species with same number of atoms, same number of valence electrons and same structure, regardless of the nature of elements involved. 2019-20. 88. Chemistry. Element X is the enthalpy change, IH, for the reaction depicted in equation 3.1. X, G, X plus, G, plus E. 3.1. The ionization enthalpy is expressed in units of kJ mol 1. We can define the second ionization enthalpy as the energy required to remove the second most loosely bound electron. It is the energy required to carry out the reaction shown in equation 3.2. X plus, G, X2 plus, G, plus E. 3.2. Energy is always required to remove electrons from an atom and hence ionization enthalpies are always positive. The second ionization enthalpy will be higher than the first ionization enthalpy because it is more difficult to remove an electron from a positively charged ion than from a neutral atom. In the same way, the third ionization enthalpy will be higher than the second and so on. The term, ionization enthalpy, if not qualified, is taken as the first ionization enthalpy. The first ionization enthalpies of elements having atomic numbers up to 60 are plotted in Fig. 3.5. The periodicity of the graph is quite striking. You will find maxima at the noble gases which have closed electron shells and very stable electron configurations. On the other hand, minima occur at the alkali metals and their low ionization enthalpies can be correlated. Fig. 3.5 Variation of first ionization enthalpies, IH, with atomic number for elements with Z is equal to 1 to 60 with their high reactivity. In addition, you will notice two trends. The first, ionization enthalpy generally increases as we go across a period and decreases as we descend in a group. These trends are illustrated in Figs. 3.6a and 3.6b, respectively, for the elements of the second period and the first group of the periodic table. You will appreciate that the ionization enthalpy and atomic radius are closely related properties. To understand these trends, we have to consider two factors: I, the attraction of electrons towards the nucleus, and 2, the repulsion of electrons from each other. The effective nuclear charge experienced by a valence electron in an atom will be less than Fig. 3.6a. First, ionization enthalpies, IH, of elements of the second period as a function of atomic number, Z, and Fig. 3.6b, IH of alkali metals as a function of Z. 3.6a, 3.6b, 2019-20. 89 Classification of elements and periodicity in proper ties. The actual charge on the nucleus because of shielding or screening of the valence electron from the nucleus by the intervening core electrons. For example, the 2s electron in lithium is shielded from the nucleus by the inner core of 1s electrons. As a result, the valence electron experiences a net positive charge which is less than the actual charge of +3. In general, shielding is effective when the orbitals in the inner shells are completely filled. This situation occurs in the case of alkali metals which have single outermost ns electron preceded by a noble gas electronic configuration. When we move from lithium to fluorine across the second period, successive electrons are added to orbitals in the same principal quantum level, and the shielding of the nuclear charge by the inner core of electrons does not increase very much to compensate for the increased attraction of the electron to the nucleus. Thus, across a period, increasing nuclear charge outweighs the shielding. Consequently, the outermost electrons are held more and more tightly, and the ionization enthalpy increases across a period. As we go down a group, the outermost electron being increasingly farther from the nucleus, there is an increased shielding of the nuclear charge by the electrons in the inner levels. In this case, increase in shielding outweighs the increasing nuclear charge, and the removal of the outermost electron requires less energy down a group. From Fig. 3.6a, you will also notice that the first ionization enthalpy of boron, Z is equal to 5, is slightly less than that of beryllium, Z is equal to 4, even though the former has a greater nuclear charge. When we consider the same principal quantum level, an s electron is attracted to the nucleus more than a p electron. In beryllium, the electron removed during the ionization is an s electron, whereas the electron removed during ionization of boron is a p electron. The penetration of a 2s electron to the nucleus is more than that of a 2p electron. Hence the 2p electron of boron is more shielded from the nucleus by the inner core of electrons than the 2s electrons of beryllium. Therefore, it is easier to remove the 2p electron from boron compared to the removal of a 2s electron from beryllium. Thus, boron has a smaller first ionization enthalpy than beryllium. Another anomaly is the smaller first ionization enthalpy of oxygen compared to nitrogen. This arises because in the nitrogen atom, 3 2p electrons reside in different atomic orbitals, Hund's rule, whereas in the oxygen atom, 2 of the 4 2p electrons must occupy the same 2p orbital, resulting in an increased electron-electron repulsion. Consequently, it is easier to remove the fourth 2p electron from oxygen than it is to remove one of the 3 2p electrons from nitrogen. Problem 3.6. The first ionization enthalpy, IH, values of the third period elements, Na, Mg and Psi are respectively 496, 737 and 786 kJ mol1. Predict whether the first IH value for L will be more close to 575 or 760 kJ mol1. Justify your answer. Solution: it will be more close to 575 kJ mol1. The value for L should be lower than that of Mg because of effective shielding of 3p electrons from the nucleus by 3s electrons. D. Electron gain enthalpy when an electron is added to a neutral gaseous atom, X, to convert it into a negative ion. The enthalpy change accompanying the process is defined as the electron gain enthalpy, EGH. Electron gain enthalpy provides a measure of the ease with which an atom adds an electron to form an ion, as represented by equation 3.3. X, G, plus EX, G. 3.3. Depending on the element, the process of adding an electron to the atom can be either endothermic or exothermic. For many elements, energy is released when an electron is added to the atom and the electron gain enthalpy is negative. For example, group 17 elements, the halogens, have very high negative electron gain enthalpies because they can attain stable noble gas electronic configurations by picking up an electron. On the other hand, noble gases have 2019 to 20. Chemistry large positive electron gain enthalpies because the electron has to enter the next higher principal quantum level, leading to a very unstable electronic configuration. It may be noted that electron gain enthalpies have large negative values toward the upper right of the periodic table preceding the noble gases. The variation in electron gain enthalpies of elements is less systematic than for ionization enthalpies. As a general rule, electron gain enthalpy becomes more negative with increase in the atomic number across a period. The effective nuclear charge increases from left to right across a period, and consequently it will be easier to add an electron to a smaller atom since the added electron on an average would be closer to the positively charged nucleus. We should also expect electron gain enthalpy to become less negative as we go down a group because the size of the atom increases and the added electron would be farther from the nucleus. This is generally the case, Table 3.7. However, electron gain enthalpy of O or F is less negative than that of the succeeding element. This is because when an electron is added to O or F, the added electron goes to the smaller n is equal to 2 quantum level and suffers significant repulsion from the other electrons present in this level. For the n is equal to 3 quantum level, S or Cl, the added electron occupies a larger region of space and the electron-electron repulsion is much less. Problem 3.7. Which of the following will have the most negative electron gain enthalpy and which the least negative? P, S, Cl, F. Explain your answer. Solution: electron gain enthalpy generally becomes more negative across a period as we move from left to right. Within a group, electron gain enthalpy becomes less negative down a group. However, adding an electron to the 2p orbital leads to greater repulsion than adding an electron to the larger 3p orbital. Hence the element with most negative electron gain enthalpy is chlorine. The one with the least negative electron gain enthalpy is phosphorus. Electronegativity, a qualitative measure of the ability of an atom in a chemical compound to attract shared electrons to itself, is called electronegativity. Unlike ionization enthalpy and electron gain enthalpy, it is not a measurable quantity. However, a number of numerical scales of electronegativity of elements, viz., Pauling scale, Malykhanov scale, or Radii scale, have been developed. The one which is the most asterisk in many books, the negative of the enthalpy change for the process depicted in equation 3.3, is defined as the electron affinity, AE, of the atom under consideration. If energy is released when an electron is added to an atom, the electron affinity is taken as positive, contrary to thermodynamic convention. If energy has to be supplied to add an electron to an atom, then the electron affinity of the atom is assigned a negative sign. However, electron affinity is defined as absolute zero and, therefore, at any other temperature, T, heat capacities of the reactants and the products have to be taken into account in H is equal to AE52 RT. Table 3.7 Electron gain enthalpies asterisk, kJ mol 1, of some main group elements H73 He plus 48 Li 60 O 141 Fluor 328 Na plus 116 Na 53 S 200 Close 349 AR plus 96 K 48 Say 195 BR 325 KR plus 96 RB 47 TE 190 I 295 XE plus 77 CS 46 PO 174 at 270 RN plus 68 Group 1 H Group 16 H Group 17 H Group 0 H 2019 to 20. 91 Classification of elements and periodicity in properties widely used is the Pauling scale. Linus Pauling, an American scientist, in 1922 assigned arbitrarily a value of 4.0 to fluorine, the element considered to have the greatest ability to attract electrons. Approximate values for the electronegativity of a few elements are given in Table 3.8. The electronegativity of any given element is not constant, it varies depending on the element to which it is bound. Though it is not a measurable quantity, it does provide a means electrons and the nucleus increases as the atomic radius decreases in a period. The electronegativity also increases. On the same account, electronegativity values decrease with the increase in atomic radii down a group. The trend is similar to that of ionization enthalpy. Knowing the relationship between electronegativity and atomic radius, can you now visualize the relationship between electronegativity and nonmetallic properties? Atom, period 2. Li BBC NOF electronegativity 1.0 1.5 2.0 2.5 3.0 3.5 4.0 atom, period 3, Na MgL Psi PSCl electronegativity 0.9 1.2 1.5 1.8 2.1 2.5 3.0 Table 3.8 I. Electronegativity values, on Pauling scale, across the periods atom electronegativity, group I, value, group 17, Value Li 1.0 F 4.0 Na 0.9 Cl 3.0 K 0.8 Br 2.8 Rb 0.8 I 2.5 Ca 0.7 at 2.2 Table 3.8 B. Electronegativity values, on Pauling scale, down a family of predicting the nature of force that holds a pair of atoms together, a relationship that you will explore later. Electronegativity generally increases across a period from left to right, say from lithium to fluorine, and decrease down a group, say from fluorine to astatine, in the periodic table. How can these trends be explained? Can the electronegativity be related to atomic radii, which tend to decrease across each period from left to right, but increase down each group? The attraction between the outer, or valence, Fig. 3.7. The periodic trends of elements in the periodic table 2019-20. Chemistry. Nonmetallic elements have strong tendency to gain electrons. Therefore, electronegativity is directly related to that nonmetallic properties of elements. It can be further extended to say that the electronegativity is inversely related to the metallic properties of elements. Thus, the increase in electronegativities across a period is accompanied by an increase in nonmetallic properties, or decrease in metallic properties, of elements. Similarly, the decrease in electronegativity down a group is accompanied by a decrease in nonmetallic properties, or increase in metallic properties, of elements. All these periodic trends are summarized in Figure 3.7. 3rd July 2002. Periodic trends in chemical properties. Most of the trends in chemical properties of elements, such as diagonal relationships, inert pair effect, effects of lanthanoid contraction, etc., will be dealt with along the discussion of each group in later units. In this section we shall study the periodicity of the valence state shown by elements and the anomalous properties of the second period elements, from lithium to fluorine. Periodicity of valence or oxidation states. The valence is the most characteristic property of the elements and can be understood in terms of their electronic configurations. The valence of representative elements is usually, though not necessarily, equal to the number of electrons in the outermost orbitals and or equal to 8 minus the number of outermost electrons as shown below. Nowadays the term oxidation state is frequently used for valence. Consider the two oxygen-containing compounds, of 2 and Na2O. The order of electronegativity of the three elements involved in these compounds is F, O, Na. Each of the atoms of fluorine, with outer group 1st February 2013, 14, 15, 16, 17, 18, number of valence 1, 2, 3, 4, 5, 6, 7, 8, electron valence 1, 2, 3, 4, 3, 5, 2, 6, 1, 7, 0, 8, electronic configuration 2s22p5, shares 1 electron with oxygen in the of2 molecule. Being highest electronegative element, fluorine is given oxidation state 1. Since there are two fluorine atoms in this molecule, oxygen with outer electronic configuration 2s22p4 shares 2 electrons with fluorine atoms and thereby exhibits oxidation state +2. In Na2O, oxygen being more electronegative accepts 2 electrons, one from each of the two sodium atoms and, thus, shows oxidation state 2. On the other hand, sodium with electronic configuration 3s1 loses 1 electron to oxygen and is given oxidation state +1. Thus, the oxidation state of an element in a particular compound can be defined as the charge acquired by its atom on the basis of electronegative consideration from other atoms in the molecule. Problem 3.8. Using the periodic table, Predict the formulas of compounds which might be formed by the following pairs of elements: A. Silicon and bromine, B. Aluminium and sulfur. Solution: A. Silicon is group 14 element with a valence of 4. Bromine belongs to the halogen family with a valence of 1. Hence the formula of the compound formed would be Br4. B. Aluminium belongs to group 13 with a valence of 3. Sulfur belongs to group 16 elements with a valence of 2. Hence, the formula of the compound formed would be Al2S3. Some periodic trends observed in the valence of elements, hydrides and oxides, are shown in Table 3.9. Other such periodic trends which occur in the chemical behavior of the elements are discussed elsewhere in this book. 2019-20. Classification of elements and periodicity in properties. There are many elements which exhibit variable valence. This is particularly characteristic of transition elements and actinoids, which we shall study later. B. Anomalous properties of second period elements. The first element of each of the groups 1, lithium, and 2, beryllium, and groups 13 to 17, boron to fluorine, differs in many respects from the other members of their respective group. For example, lithium, unlike other alkali metals, and beryllium, unlike other alkaline earth metals, form compounds with pronounced covalent character. The other members of these groups predominantly form ionic compounds. In fact, the behavior of lithium and beryllium is more similar with the second element of the group 1st February 2013 14 15 16 17 formula LiHB2H6CH4NH3H2OHF of hydride Na CH2LH3H2SH4PH3H2CHBrSNH4SBH3H2 2Te high formula Li2OMgOB2O3CO2N2O3, N2O5 of oxide Na2OCaol2O3CO2P4O6, P4O10 So3Cl2O7K2OSROGA2O3 GO2 as2O5 SeO3BaO into O3 SNO2 Sb2O3. Sb2O5 TeO3 PbO2 by 2O3 Table 3.9 Periodic trends in valence of elements as shown by the formulas of their compounds. Property element metallic radius mpm Li BB1521188 Na Mgl186160143 Li B ionic radius m plus pm 7631 Na Mg100 and 272 following group I, magnesium and aluminium, respectively. This sort of similarity is commonly referred to as diagonal relationship in the periodic properties. What are the reasons for the different chemical behavior of the first member of a group of elements in the S and P blocks compared to that of the subsequent members in the same group? The anomalous behavior is attributed to their small size, large charge radius ratio and high electronegativity of the elements. In addition, the first member of group has only 4 valence orbitals, 2s and 2p, available for bonding, whereas the second member of the groups have 9 valence orbitals, 3s 3p 3d. As a consequence of this, the maximum covalency of the first member of each group is 4, e.g., boron can only form Bf4, whereas the other members of the groups can expand their valence shell to accommodate more than 4 pairs of electrons, e.g., aluminium F6 forms. Furthermore, the first member of p block elements displays greater ability to form p-pi multiple bonds to itself, e.g., C is equal to C, CC, N is equal to N, Nu, and to other second period elements, e.g., C is equal to O, C is equal to N, Cn, N is equal to O, compared to subsequent members of the same group. 2019 to 20. 94 Chemistry Problem 3.9 are the oxidation state and covalency of Al in AlCl, H2O, 5, 2 plus same. Solution: no. The oxidation state of Al is +3 and the covalency is 6. 3rd July 2003 Periodic trends and chemical reactivity. We have observed the periodic trends in certain fundamental properties such as atomic and ionic radii, ionization enthalpy, electron gain enthalpy and valence. We know by now that the periodicity is related to electronic configuration. That is, all chemical and physical properties are a manifestation of the electronic configuration of elements. We shall now try to explore relationships between these fundamental properties of elements with their chemical reactivity. The atomic and ionic radii, as we know, generally decrease in a period from left to right. As a consequence, the ionization enthalpies generally increase, with some exceptions as outlined in section 3.7.1, and electron gain enthalpies become more negative across a period. In other words, the ionization enthalpy of the extreme left element in a period is the least and the electron gain enthalpy of the element on the extreme right is the highest negative. Note: noble gases having completely filled shells have rather positive electron gain enthalpy values. This results into high chemical reactivity at the two extremes and the lowest in the center. Thus, the maximum chemical reactivity at the extreme left, among alkali metals, is exhibited by the loss of an electron leading to the formation of a cation, and at the extreme right, among halogens, shown by the gain of an electron forming an anion. This property can be related with the reducing and oxidizing behavior of the elements, which you will learn later. However, here it can be directly related to the metallic and non-metallic character of elements. Thus, the metallic character of an element, which is highest at the extremely left, decreases and the non-metallic character increases while moving from left to right across the period. The chemical reactivity of an element can be best shown by its reactions with oxygen and halogens. Here, we shall consider the reaction of the elements with oxygen only. Elements on two extremes of a period easily combine with oxygen to form oxides. The normal oxide formed by the element on extreme left is the most basic, e.g., Na2O, whereas that formed by the element on extreme right is the most acidic, e.g., Cl2O7. Oxides of elements in the center are amphoteric, e.g., L2O3, S2O3, or neutral, e.g., Co, No, N2O. Amphoteric oxides behave as acidic with bases and as basic with acids, whereas neutral oxides have no acidic or basic properties. Problem 3.10 show by a chemical reaction with water that Na2O is a basic oxide and Cl2O7 is an acidic oxide. Solution: Na2O with water forms a strong base whereas Cl2O7 forms strong acid. Na2O plus H2O2 now HCl2O7 plus H2O2 for their basic or acidic nature can be qualitatively tested with litmus paper. Among transition metals, 3D series, the change in atomic radii is much smaller as compared to those of representative elements across the period. The change in atomic radii is still smaller among inner transition metals. For F series, the ionization enthalpies are 2019 to 20. 95 Classification of elements and periodicity in properties intermediate between those of S and P blocks. As a consequence, they are less electropositive than group 1 and 2 metals. In a group, the increase in atomic and ionic radii with increase in atomic number generally results in a gradual decrease in ionization enthalpies and a regular decrease, with exception in some third period elements as shown in section 3.7.1 d, in electron gain enthalpies in the case of main group elements. Thus, the metallic character increases down the group and non-metallic character decreases. This trend can be related with their reducing and oxidizing property, which you will learn later. In the case of transition elements, however, a reverse trend is observed. This can be explained in terms of atomic size and ionization enthalpy. Summary: in this unit, you have studied the development of the periodic law and the periodic table. Mendeleev's periodic table was based on atomic masses. Modern periodic table arranges the elements in the order of their atomic numbers in 7 horizontal rows, periods, and 18 vertical columns, groups or families. Atomic numbers in a period are consecutive, whereas in a group they increase in a pattern. Elements of the same group have similar valence shell electronic configuration and, therefore, exhibit similar chemical properties. However, the elements of the same period have incrementally increasing number of electrons from left to right, and, therefore, have different valencies. 4 types of elements can be recognized in the periodic table on the basis of their electronic configurations. These are S block, P block, D block and F block elements. Hydrogen with 1 electron in the 1s orbital occupies a unique position in the periodic table. Metals comprise more than 78% of the known elements. Non-metals, which are located at the top of the periodic table, are less than 20 in number. Elements which lie at the borderline between metals and non-metals, e.g., Psi, Ge, As, are called metalloids or semi-metals. Metallic character increases with increasing atomic number in a group, whereas decreases from left to right in a period. The physical and chemical properties of elements vary periodically with their atomic numbers. Periodic trends are observed in atomic sizes, ionization enthalpies, electron gain enthalpies, electronegativity and valence. The atomic radii decrease while going from left to right in a period and increase with atomic number in a group. Ionization enthalpies generally increase across a period and decrease down a group. Electronegativity also shows a similar trend. Electron gain enthalpies, in general, become more negative across a period and less negative down a group. There is some periodicity in valence. For example, among representative elements, the valence is either equal to the number of electrons in the outermost orbitals or 8 minus this number. Chemical reactivity is highest at the 2 extremes of a period and is lowest in the center. The reactivity on the left extreme of a period is because of the ease of electron loss, or low ionization enthalpy. Highly reactive elements do not occur in nature in free state, they usually occur in the combined form. Oxides formed of the elements on the left are basic and of the elements on the right are acidic in nature. Oxides of elements in the center are amphoteric or neutral. 2019-20 96 Chemistry Exercises 3.1 What is the basic theme of organization in the periodic table? 3.2 Which important property did Mendeleev use to classify the elements in his periodic table, and did he stick to that? 3.3 What is the basic difference in approach between the Mendeleev's periodic law and the modern periodic law? 3.4 On the basis of quantum numbers, justify that the sixth period of the periodic table should have 32 elements. 3.5 In terms of period and group, where would you locate the element with Z is equal to 114? 3.6 Write the atomic number of the element present in the third period and 17th group of the periodic table. 3.7 Which element do you think would have been named by I. Lawrence Berkeley Laboratory? 2. Seaborg's group. 3.8 Why do elements in the same group have similar physical and chemical properties? 3.9 What does atomic radius and ionic radius really mean to you? 3.10 How do atomic radius vary in a period and in a group? How do you explain the variation? 3.11 What do you understand by isoelectronic species? Name a species that will be isoelectronic with each of the following atoms or ions: I, F, 2, Ar, 3, Mg2+, 4, Rb+. 3.12 Consider the following species: N3, O2, F, Na+, Mg2+, and L3+. A. What is common in them? B. Arrange them in the order of increasing ionic radii. 3.13 Explain why cations are smaller and anions larger in radii than their parent atoms. 3.14 What is the significance of the terms isolated gaseous atom and ground state while defining the ionization enthalpy and electron gain enthalpy? Hint: requirements for comparison purposes. 3.15 Energy of an electron in the ground state of the hydrogen atom is 2.18 × 1018 J. Calculate the ionization enthalpy of atomic hydrogen in terms of J mol 1. Hint: apply the idea of mole concept to derive the answer. 3.16 Among the second period elements, the actual ionization enthalpies are in the order Li, B, B, C, O, N, F, N. Explain why I, B has higher IH than B, 2, O has lower IH than N and F. 2019-20. 97 Classification of elements and periodicity in properties. 3.17 How would you explain the fact that the first ionization enthalpy of sodium is lower than that of magnesium but its second ionization enthalpy is higher than that of magnesium? 3.18 What are the various factors due to which the ionization enthalpy of the main group elements tends to decrease down a group? 3.19 The first ionization enthalpy values, in kJ mol 1, of group 13 elements are BLGA in TL 801577 and 79500 and 58500 and 89. How would you explain this deviation from the general trend? 3.20 Which of the following pairs of elements would have a more negative electron gain enthalpy? I, O or F? 2. F or Cl. 3.21 Would you expect the second electron gain enthalpy of O as positive, more negative or less negative than the first? Justify your answer. 3.22 What is the basic difference between the terms electron gain enthalpy and electronegativity? 3.23 How would you react to the statement that the electronegativity of N on Pauling scale is 3.0 in all the nitrogen compounds? 3.24 Describe the theory associated with the radius of an atom as it A. gains an electron, B. loses an electron. 3.25 Would you expect the first ionization enthalpies for two isotopes of the same element to be the same or different? Justify your answer. 3.26 What are the major differences between metals and nonmetals? 3.27 Use the periodic table to answer the following questions. A. Identify an element with 5 electrons in the outer subshell. B. Identify an element that would tend to lose 2 electrons. C. Identify an element that would tend to gain 2 electrons. D. Identify the group having metal, nonmetal, liquid as well as gas at the room temperature. 3.28 The increasing order of reactivity among group 1 elements is Li, Na, K, Rb, Cs, whereas that among group 17 elements is F, Ci, Br, I. Explain. 3.29 Write the general outer electronic configuration of S, P, D and F block elements. 3.30 Assign the position of the element having outer electronic configuration I, Ns2 Np4 for N is equal to 3, 2, N-1, D2 Ns2 for N is equal to 4, and 3, N-2, F7, N-1, D1 Ns2 for N is equal to 6, in the periodic table. 2019-20. 98 Chemistry 3.31 The first, IH1, and the second, IH2, ionization enthalpies, in kJ mol 1, and the EGH, electron gain enthalpy, in kJ mol 1, of a few elements are given below. Elements H1, H2, EGH I520, 7300 419, 305148 31681, 337432841008, 1846295 V2372, 5251 plus 4863738, 145140 Which of the above elements is likely to be a. The least reactive element, b. the most reactive metal, c. the most reactive nonmetal, d. the least reactive nonmetal, e. the metal which can form a stable binary halide of the formula Mx2, X is equal to halogen, f. the metal which can form a predominantly stable covalent halide of the formula Mx, X is equal to halogen. 3.32 Predict the formulas of the stable binary compounds that would be formed by the combination of the following pairs of elements: a. lithium and oxygen, b. magnesium and nitrogen, c. aluminium and iodine, d. silicon and oxygen, e. phosphorus and fluorine, f. element 71 and fluorine. 3.33 In the modern periodic table, the period indicates the value of a. atomic number, b. atomic mass, c. principal quantum number, d. azimuthal quantum number. 3.34 Which of the following statements related to the modern periodic table is incorrect? A. The p block has 6 columns, because a maximum of 6 electrons can occupy all the orbitals in a p shell. B. The d block has 8 columns, because a maximum of 8 electrons can occupy all the orbitals in a d subshell. C. Each block contains a number of columns equal to the number of electrons that can occupy that subshell. D. The block indicates value of azimuthal quantum number, L, for the last subshell that received electrons in building up the electronic configuration. 2019-20. 99 Classification of elements and periodicity in properties. 3.35 Anything that influences the valence electrons will affect the chemistry of the element. Which one of the following factors does not affect the valence shell? A. Valence principal quantum number, N. B. Nuclear charge, Z. C. Nuclear mass, D. Number of core electrons. 3.36 The size of isoelectronic species, F, Na and Na plus is affected by A. Nuclear charge, Z, B. Valence principal quantum number, N, C. Electron-electron interaction in the outer orbitals, D. None of the factors because their size is the same. 3.37 Which one of the following statements is incorrect in relation to ionization enthalpy? A. Ionization enthalpy increases for each successive electron. B. The greatest increase in ionization enthalpy is experienced on removal of electron from core noble gas configuration. C. End of valence electrons is marked by a big jump in ionization enthalpy. D. Removal of electron from orbitals bearing lower n value is easier than from orbital having higher n value. 3.38 Considering the elements B, L, Mg, and K, the correct order of their metallic character is A, B, L, Mg, K, B, L, Mg, B, K, C, Mg, L, K, B, D, K, Mg, L, B. 3.39 Considering the elements B, C, N, F, and Psi, the correct order of their non-metallic character is A, B, C, Psi, N, F, B, Psi, C, B, N, F, C, F, N, C, B, Psi, D, F, N, C, Psi, B. 3.40 Considering the elements F, Cl, O and N, the correct order of their chemical reactivity in terms of oxidizing property is A, F, Cl, O, N, B, F, O, Cl, N, C, Cl, F, O, N, D, O, F, N,